Again, there are like a number of classifications, but we are going to consider only the most vital ones and the only important ones that you can consider for your curriculum. Okay, so first of all, as you can see, the first head of this classification goes as Turing machine with stay option. So, what is this? Normally, we have seen that a Turing machine has a read write head that can move either in the left direction or in the right direction. So, this is a special variant of Turing machine in which we have S, a stay option, where a read write head will be staying in the position it was. That is, it won't be moving left or right, but it will be staying right in the position it was in the previous step. Okay. So, this is nothing but a Turing machine with stay option. Okay, so actually I missed a point, sorry. One important point which I should tell you all before I start with this classification is whatever variant of Turing machine we are using, we are noticing over here, uh, they have got certain modifications in their construction, but from the power point of view, that is their effectiveness or their power, they will be same as a standard Turing machine that we have came across. Okay, I'm repeating, any modification in the standard Turing machine does not changes the power of the Turing machine. There is again, how are we judging the power of a Turing machine? So, power of a Turing machine is actually determined depending upon the language or set of languages it is accepted. It is accepting. So, even if we change the certain configurations of Turing machine, we come across various variants of Turing machine, the power will remain same. That is, it will always accept the same set of languages that is accepted by a standard Turing machine. Nothing more can be accepted by making these modifications. Okay. So this was a very important point to say. So we have already seen a Turing machine with stay option. Next, a Turing machine with a semi-infinite tape. See, students, we have already seen in our previous lectures that Turing machine consists of a tape, and the tape is actually an infinite tape in both the direction, that is in left direction as well as right direction. It is an infinite tape. Okay. So in this particular classification of Turing machine, we are actually restricting the left hand side of the tape. That is, the left hand side of the tape, as you can see here, the left hand side of the tape is not infinite anymore. It has been restricted. Only the right hand side is infinite, that is, you can go along in an infinite direction along your right hand side, but the left hand side has been constrained. It is not infinite anymore. So this is a semi infinite tape. A Turing machine with a semi-infinite tape. Okay, fine. So next, moving on with the multi-tape Turing machine. Again, this is quite an important variant of Turing machine. So, how can we simply describe or define a multi-tape Turing machine, or what is the basic difference between a normal Turing machine and a multi-tape Turing machine? So, as the name suggests, a multi-tape Turing machine has got multiple tapes. Okay, so as you can see in this diagram, we have tape 1, tape 2, tape 3. Only one finite control is there, and each read write head goes for each of the tapes. Now, as the transition function is concerned, if you look into this transition function, you can see that it is mapping from q is the state, cross tau to the power n. Tau is what? If you remember, tau was the set of the tape symbols, right? So we are in state Q, we encounter a tape symbol T. Why is this to the power n? This to the power n is for the number of tapes. N is equal to number of tapes. Here we have 3 tapes, so n will be equal to 3. That is, at a particular point of time, we will consider the state in which the Turing machine is and the tape symbol of all these tapes. That is why we are writing to the power n. And then it will change, or the state transition will occur in such a way, that is, the state will change q, tau to the power n. Again, the tape symbol in each of the tapes will get modified if required, and l comma r to the power n. That is, the read write head will move either towards the left or towards the right in all these tapes. Therefore, we have again written to the power n. So whatever is happening over here is happening in a power of n, where n is your number of tapes, since this is a multi-tip Turing machine. Okay. So students, one thing that I had started with was that power of a Turing machine is unaffected. Right, I had said that whatever modifications we make in a Turing machine, the power of it will always remain unaffected. Okay, but what about the time complexity? Okay, for a particular given problem, for a particular given language, it might happen that when we are using a multi-tip Turing machine, the time taken is lesser than that of the scenario when a standard Turing machine is used. That is what I have written here. This power of a Turing machine is unaffected, right? But the time taken to accept any string might be different for a multi-tip Turing machine. And in most of the cases, the time taken actually reduces because it has got multiple tapes. Okay, we will see how. We'll actually take an example and see how. Okay. So let's take this very simple example, a to the power n and b to the power n, a to the power and b to the power n. You have seen this example multiple number of times. You have used a PDA to construct this. You have used a Turing machine to construct this, right? So in a standard Turing machine, what happens? The logic that we use, we have a, b, b, b inside that tape. I have not drawn the tape actually. Just consider we have a tape and a, b, b, b are tape symbols. Now the standard approach that we follow is we will mark this a as x and we will move rightwards. Again we will mark this b as y, and again we will move leftwards, mark this a as x, again go towards right, mark this b as y, and this will go on, right? So we are actually moving to and fro towards left and right continuously until all the a's and b's are exhausted, right? So if you see, for a single a and a single b, we have to traverse all these symbols. That is, if n is the number of symbols, so we have to traverse all these n symbols for a single a, single b, right? And again, for all, like exhausting all these symbols, again we have to do it n number of times. So the total complexity turns out to be order of n square. Why n square? Because for each symbol n movements, and again for exhausting all these n symbols, again n. So n cross n square. Order of n square is the time complexity required for accepting this language by a Turing machine. On the contrary, in a multi-tip Turing machine, what happens? See, we have two tapes over here, right? This one tape 1 and tape 2 I have not written. Consider this as tape 1 and consider this as tape 2. So we are putting the symbols. We have A, B, B in tape 1. Again, we are putting the same set of symbols A, B, B in tape 2 as well. The first tape, that is copy. That is what I said. We will just copy the same thing in the second tape, tape 2. So copy takes order of n time. Simple. I guess no explanation is required for this. What is the second step? Set the read-write head in the suitable position. So what is the suitable position? For the first tape, the read-write head will be in the first A, and for the second tape, the read-write head will be on the first B. Okay, so this will again take order of n time. And finally, in the third step, we are going to scan the symbols. Okay, so how are we going to scan the symbols? We will scan the A first and mark it as X. We will scan this B, mark it as Y. We will scan this X, scan this A as X and scan this B as Y, and we are done. And it will take only order of n time, because we are not moving to and fro, and we are not like supposed to exhaust all the symbols in an intersection. Okay, so as we can see, order of n, order of n, order of n, it is done in a linear time. It is not taking order of n square, but it will take time complexity which is an order of n. So here the time is decreased. Again I'll say that the power is not decreased or increased. The power remains unchanged. What changes is the time that this Turing machine takes to accept a particular language. Okay. Okay, fine. We'll move on to the next classification of the special variant of Turing machine, that is jumping Turing machine. So what is a jumping Turing machine? As this figure suggests, normally what happens in a Turing machine, the read-write head moves from one cell to the next cell, right? So whenever the read-write head is moving to the left, it moves to the next cell, or it moves to the right, it moves to the next right cell. But in a jumping Turing machine, what happens? We have an extra variable n. What is this n? N is the number of steps or the number of cells that the Turing machine is supposed to jump. So the transition function looks somewhat like this: q into tau, which maps to q into tau, l comma r, and n, where n is the number of cells to the left or right, which is the which the read-write head is supposed to move. Okay, this is the basic difference. I hope it's clear. So next, moving on to multi-dimensional Turing machine. So multi-dimensional Turing machine is again very interesting construction of a standard Turing machine. Here, as you can see, the transition function goes like this. We have q into tau, which maps to q into tau into L comma R comma U comma D. What is U and D? U is upward direction, D is downward direction. So in this case, our Turing machine tape looks somewhat like this. We have a number of rows and columns, and the read-write head can not only move to the left or right direction, but it can also freely move to the upward or downward direction. This is a multi-dimensional Turing machine. Okay, again, the power of this Turing machine is same. No power enhancement is encountered. Okay. Next, we go for a multi-head Turing machine. Okay, so till now we have seen multi-dimensional, multi-tape, where we had multiple tapes and multiple dimensions, but this one is multi-head Turing machine. That is a finite control will have multiple heads going on to the same tape. That is, it can actually monitor different parts of the tape at the same point of time. So this read-write head is actually monitoring this part. This read-write head is actually reading or writing this part, and again this read-write head is monitoring this part. Okay, so as you can see, we have multiple read-write heads over here. Okay, so finally, non-deterministic Turing machine. So what is a non-deterministic Turing machine? As you can see, it's quite easy. You all already know what is the meaning of a non-determinism. That is, for a particular transition function, we have options. We can actually move on to state 1, or we can move on to state 2, or something like that. Okay, so that is what is being depicted in this particular transition function. That is, q cross tau is actually mapped to a power set of q cross tau cross l comma r. That is, it will it can move to various states, or it can move to various states with various directions. Okay, it may be the it may be a scene that you are in state q1 with tape symbol a, and you are moving to state q2. The tape symbol is remaining same, and you're moving to right direction. Okay, this is one transition function. Again, for the same state q1 and for the same state symbol q same tape symbol a, you actually can go to the next state q3. The state symbol, the tape symbol may change to b, and you may move to left direction. That is, it's same as your non-deterministic finite automata, where you can actually go to two different states on getting the same input. Here also, on getting the same tape symbol, you can move to two different states with two different direction of read-write head. This is the basic difference. Okay, now again, students, comparing the power of a deterministic Turing machine and a non-deterministic Turing machine, we can say that both of them are equally powerful. As we have seen for deterministic finite automata and non-deterministic finite automata also, they can actually accept the same set of strings. There is no such string which cannot be accepted by deterministic finite automata, but it is accepted by non-deterministic finite automata. Similarly, here also you cannot get any such string which is accepted by non-deterministic Turing machine but is not accepted by deterministic Turing machine, or vice versa. That is, the set of languages that is accepted is same for both, and therefore we can say that they are equally powerful. There can be no comparison of power between a deterministic Turing machine and a non-deterministic Turing machine. Okay, so guys, we will continue with linear bounded automata in our next lecture. Thank you so much.